Done, sir.
Fawaz, done.
Yes, sir.
Saifullah,
Yes, sir, done.
okay. So this is all about thermal properties of matter and Newton's law of cooling. So we have just finished this entire chapter. So let me start with thermodynamics, the new chapter. First, what do you mean by thermodynamics? So you'll say this particular word consists of two parts. One is therm and the second is dynamics. Therm means heat and dynamics means motion. So you'll say the study of motion or the study of heat in motion and conversion of heat from one form to another is called thermodynamics. So in this entire chapter, we mainly discuss about flow of heat and its conversion into different other form of energy as well. So thermodynamics basically defines you the study of flow of heat and its conversion into other form of energy. Now, in this particular part, let me define you some basic concept related to this thermodynamics. First is thermodynamical variable. There are some physical quantity, suppose number of moles, pressure, volume, temperature, which defines the condition of a gas at any particular instant by a relationship in between them. So these physical quantity together is called thermodynamical variable, or you will say the physical quantity on which state or condition of gas may depend upon. Is it clear? So thermodynamical variable is the physical quantity, just as number of moles, pressure, volume, temperature, which defines condition of gas. Mamuna, any doubt?
No, sir.
Okay. So to relate in between these thermodynamical variable, we may define equation of state. Equation of state is relationship in between thermodynamical variable to define the condition of gas at any instant. So equation of state is the relationship between thermodynamical variable which defines the state or condition of gas at any instant. Saifullah, any doubt? Aisha?
No, sir.
Okay. So we mainly have first equation, PV raised to x is equals to constant. Second, we may write 1 by x v equals to constant. And in third part, PV is equals to nRT, ideal gas equation. On the basis of different condition, the value of x for these two expression may get changed. I will define you in different various process. And this is the ideal gas equation, which is defined for a particular condition related to these two different parts. Fawaz, any doubt?
No, sir.
Okay, first write it down till this part. How many of you have done thermodynamics in chemistry? Marine,
Yes, sir.
you have done thermodynamics in chemistry?
No, sir.
Okay. You all have done?
Yes.
Yes, sir.
Saifullah, done?
Yes, sir.
Now, related to this equation of state, we may define molar specific heat constant or capacity, which I had already defined in last chapter, thermal properties of matter. But mainly we have to define for this part. So to state, the amount of energy or heat energy is required to change 1 mole of gas by 1 degree centigrade or 1 Kelvin at given condition. So we may define the amount of heat is required to change temperature of 1 mole gas by 1 Kelvin or 1 degree centigrade at given condition. It may depend upon their process, isobaric, isoporic, isothermal, adiabatic. So we can define dq equals to number of moles into C times dt, where this C is called molar specific heat constant, which may also be written like C equals to R divided by gamma minus 1 minus R divided by X minus 1. In this particular expression, R is universal gas constant. You must have learned about it in your chemistry. This is equals to 25 by 3 or 8.314 joule per mole per Kelvin, a constant value. Next, X is the expression what we obtain from that ever part, Pv to the power X or P to the power 1 by X, V is equals to constant. I'm defining what do you mean by this particular gamma. So in general, specific heat of any gas is defined by this expression. So it is the general expression of molar specific heat constant for any different process. Is it clear?
Yes, sir.
Yes.
Okay. Now let me define you. What do you mean by this gamma? First, let me define you. What do you mean by degree of freedom? Suppose you have a particle, monoatomic particle, just as helium. This. If you have diatomic molecule, just as hydrogen, oxygen, nitrogen, like this. Or you'll have triatomic, just as water molecule, which having bent shape, like this. Now, if I ask you to define energy of this monoatomic particle, so you'll say this monoatomic particle having tendency to move along 3 different coordinate axes. It may go along x-axis, along y-axis, or along z-axis as well. So we can say this monoatomic particle will have translational energy on moving along respective coordinate axes, like these 3 axes. Is it clear?
Yes.
In second part, if I ask you to define in how many directions this diatomic molecule may have energy contained with it. So you'll say it also tend to go along x-axis, y-axis, as well as z-axis, and it also have some rotational energy as well. It may rotate along this axis, it may rotate along this axis, but there will be no rotation possible along this y-axis. Since suppose you have body like this, You may rotate it along this vertical axis. You may rotate along this horizontal axis, but you can't rotate or define rotation along this axis, since this is point object for which there will be no rotation possible. Is it clear? Saifullah, any doubt?
No, sir.
Similarly, if I ask you in how many direction this third part or this bent molecule would have contained energy in it. Saifullah, try to calculate. You'll say it must have translational energy along x-axis, along y-axis, as well as along z-axis. It means this bent shape must move along these respective coordinate axes along translational motion. Mamuna, is it clear?
Yes, sir.
Will there be any rotation possible to this part? So you'll say yes, it may rotate along this axis, it may rotate along this axis, or it may rotate along this axis as well. So we can say this bent shape molecule will have 3 translational energy and 3 rotational energy. So in total, it will have 6 different ways of energy. Saifullah, is it clear?
Sir, can you explain translation energy and rotation energy again?
Okay, just 1 minute. Suppose you have 3 like this or bent shape like this. So this particular configuration may bend along this axis. It may bend along this axis, or it may rotate along z-axis as well. Suppose this is any triangle. If you are seeing along this axis, it may rotate along this way. If you are visualizing along this axis, it may rotate along this way. And along z-axis, it may rotate along this way. So we can say this bent shape will have 3 different rotation and 3 different translation. Is it clear?
Yes, sir.
So degree of freedom basically defines you in how many ways a molecule or a particle contain energy. So let me define you about this degree of freedom. It defines the coordinate or direction in which gas contain energy or gaseous particle or molecule contain energy. So in first part, for monoatomic, degree of freedom is represented by F. We have 3 degree of freedom and all are along translational part. In second term, we have 3 translational energy plus 2 rotational energy. And in third part, we have 3 translational energy and 3 rotational energy. So in total, you will say bent shape particle will have more degree of freedom as compared to monoatomic and diatomic. Saifullah, is it clear?
Yes, sir.
Aisha, any doubt?
No, sir.
Mehreen,
No, sir.
is it clear about degree of freedom?
Yes, sir.
Okay, now question will be, will this degree of freedom depend upon temperature? Mamuna, any guess?
I think in some cases.
Okay, like in monoatomic, diatomic, triatomic. Let me define you. Since degree of freedom is basically direction or ways in which these gaseous molecular particle having energy stored in it. So in monoatomic particle, there will be no change in energy on raising temperature or decreasing temperature. It will remain three different phases of energy. In second part, diatomic particle, on increasing temperature, there will be possibility of breaking down of bond or weakening of bond, which will include or which will add on another form of energy that is called vibrational energy to this part. Similarly, triatomic particle, which having connected with bond, which on increasing temperature, there will be weakening of bond. So there will be some vibrational energy attached with it. So you will say, except monoatomic particle, if you raise the temperature of system, there will be weakening of bond. So there will be additional form of energy in the form of vibrational. So degree of freedom increases with a rise in temperature. Is it clear?
Yes, sir.
Marine, any doubt?
No, sir.
So from this part, we can say on increasing temperature, vibrational energy increases due to weakening of bond. Hence, degree of freedom increases. Aisha, any doubt?
No, sir.
Saifullah, is it clear?
Yes, sir.
Now, we have to define this degree of freedom with gamma. So, gamma is called specific gas ratio, which is equals to 1 plus 2 by F. Now, if you put the value of F for monoatomic, diatomic, or triatomic, polyatomic, anything, degree of freedom increases. So on increasing degree of freedom, gamma will decreases. So in general, gamma of triatomic will be least, gamma of diatomic and gamma of monoatomic, and will be always in the range of this part. It means gamma lies in between 1 and 2. Mamuna, is it clear?
Yes, sir.
Okay, just write it down. You have done?
Yes, sir.
Mary, done?
Yes, sir.
Saifullah?
1 minute, sir. 1 minute.
Okay. You may write this T is for translational. This R is for rotational. Aisha, any doubt?
No, sir.
Saifullah, done?
Yes, done.
Okay. Now, the next part is what do you mean by real gas and ideal gas? Suppose you have gas, real gas, and ideal gas. Mamuna, any idea?
No, sir.
Suppose you have gaseous particle like this. So if there is interaction between these two particles, so due to interaction, they will have some potential energy in this particular system. So if there is interaction between particle of gas, then it will have some kinetic energy due to their interaction. And also, since this particular system may have some temperature which is greater than 0 Kelvin, so this molecule or this gaseous particle will have some thermal kinetic energy, or you'll say kinetic energy due to temperature. Now, if you add these two energy to get total energy stored in this gaseous particle, it is termed as internal energy. So internal energy is defined by U, which is sum of kinetic energy plus potential energy. Mehreen, is it clear? Saifullah, any doubt?
No, sir.
Now suppose if there is gaseous particle in which there is no interaction in between them. If there is no interaction between particle of gas. So in this case, you will say potential energy in this particular system will be 0. So it will have only kinetic energy due to temperature. Mamuna, is it clear?
Yes, sir.
Now, if you add these two energy to define internal energy of this particular gas, so you can say internal energy equals to just kinetic energy, and it will be defined by temperature of this particular system only, since there is no interaction between the particle, or you can say there will be no potential energy stored in this particular system. Aisha, any doubt?
No, sir.
So you'll be asked at which condition real gas will tend to behave as ideal gas. So for real gas to behave as ideal gas, first condition is to be there will be least interaction in between the particle. So if particle will have to get least interacted, there must be large separation in between them. Is it clear? Saifullah?
Can you repeat?
Okay. Since if you have to define real gas, or if you have to relate or behave real gas as ideally, there will have no interaction between particle, or you'll say there will be least interaction in between particle. How will you decrease the interaction between particle of a gas? So you'll say by increasing their separation. If separation between particle increases, there will be lesser force of attraction between them, or there will be lesser interaction between particle of gas. So the next question is, how will you increase the separation between particle of gas? Let me remind you, in class 9th, you have done on changing pressure, we can convert the state from one part to another. If you decrease the pressure, there will be more chances of getting large space in between the particle of gas or in between particle of any matter. If you increase pressure, then separation between particles get crowded in between. So if you have to convert real gas to behave as ideal gas, there will be a decrease in pressure. Is it clear?
Yes, sir.
Next is, since temperature defines you kinetic energy, so if you increase the temperature of that particular system, particle will have more kinetic energy, more randomness, so they will get least interacted with one another. So from this, we can conclude at low pressure and high temperature, real gas will tend to behave as ideal. Aisha, is it clear?
Yes, sir.
Mehreen,
Yes, sir.
Saifullah, any doubt?
No, sir.
Mamuna?
No, sir, no doubts.
Okay, just write it down. And just remember the difference in between them. You all are done?
Yes, sir.
Saifullah, done?
No. Yes, finished.
Okay, so do you have any doubt to any one of you till this part?
No, sir.
Mehreen?
No, sir.
Okay, so let's stop here for today. In next class, we'll start zeroth law, first law, and then various process related to this part. Okay, so just revise up to this part and try to do various problems. Okay, we'll continue next class.
Okay, sir. Thank you.
Thank you.
Thank you, sir.
Thank you.